This is a little bit a big problem, but we have to be carefully doing this problem to understand so many concepts. For oxygen, at 25 degrees centigrade and at 1 atmospheric pressure, calculate number 1, the number of collisions per second per molecule. Number 2, number of collisions per cubic meter per second. Number 3, number of moles of collisions per decimeter cube per second. And here also the collision diameter is 361 picometer. See, the collision number means it is the number of collisions suffered by a single molecule per unit time per unit volume. So which is Z1 is equal to square root 2 pi sigma square C, which is the average velocity, rho, the number density. Normally the rho is substituted as P by KT. So you should understand how this rho has become P by KT. So PV is equal to nRT, P is equal to N by V RT, N is the number of moles. Therefore, number of atoms or number of moles, R is nothing but Avogadro number into Boltzmann constant. So when you do this, you are getting number of Avogadro number and the number of moles will give you total number of molecules. So number per volume is number density rho KT. This is how it has come. So P is equal to rho KT. Therefore, rho is equal to P by KT. And also, before going to the problem, we have to calculate the average velocity, which is equal to square root of 8 RT by pi into molar mass. So 8, 8.314 joule per Kelvin per mole. Again, you have to remember joule is nothing but kilogram meter square per second square into 298 Kelvin divided by 3.14 into the oxygen molecular weight 32 into 10 power minus 3 kilogram per mole. So when you substitute all these values, you are getting 444.138 meter per second. So this is the average velocity of the oxygen molecules. Now you can find out the collision number is at 1, which is equal to square root of 2, 3.14. This is the sigma, which is substituted as a 3.61 into 10 power minus 10 meter whole square into the average velocity into the rho. This is the into the number density. Number density is substituted as a pressure. No, look here. Number density, instead of number density, it is substituted as pressure and divided by K. This is T. So look here, the density is substituted in this place as P by KT. That is what is given here. This is the pressure 1.01325 into 10 power 5 Newton per meter square divided by K into T. That K Boltzmann's constant I have written as R by Na because these are all the known values. R is 8.314 joule per Kelvin per mole divided by Avogadro number 6.023 into 10 power 23 per mole. So into 298 the Kelvin. So when you substitute all these things, you are getting 6.33 into 10 power 9 per second. Therefore, the oxygen molecules, they experience 6.33 into 10 power 9 collisions per second per molecule. So now the number of collisions per cubic meter per second, you have to use another formula, which is 1 by root 2 pi sigma square average velocity into rho square. Again, you are substituting here pi sigma square average is there. You have to put rho square in this place. Instead of rho square, I'm substituting P square, KT square. And this KT square can also be substituted as Na square, R square. Na square, R square, and T square. So when you substitute all these values here, you are getting 7.7975 into 10 power 34 per meter cube per second. So in 1 meter cube volume, in 1 second, the oxygen molecules experience 7.7975 into 10 power 34 collisions. So now I am going to convert this into decimeter cube. So for decimeter cube, I have to multiply this by 10 power 3, 10 power minus 3, and per molecule, I have to divide it by the Avogadro number. So when I multiply by 10 power minus 3, I'm getting the answer for per decimeter cube. When I divide it by Avogadro number, I'm getting for per molecule. Therefore, it is 1.29 into 10 power 8 mole per decimeter cube per second. So this is the number of moles of collisions per decimeter cube per second it is taking place.